Hi, I'm Brendan Christopher Tomara. Uh, I'm going to be in charge of the classification for this group assignment. I'm going to be talking about classification. So the problem statement for classification would be identifying patterns in opioid or related fatalities is crucial for improving early detection and intervention efforts. By leveraging demographic and geographic data, a predictive model can help public health officials and policymakers target high-risk individuals and allocate resources effectively to reduce opioid-related deaths. So the objective would be build a model to predict whether there was an involvement of opioid in drug-related death based on demographic and location-based features on high-risk individuals. Oh, okay. So what's classification? Classification models are a type of machine learning model that divides data points into predefined groups called classes. Classifiers are a type of predictive modeling that learns characteristics from input data and learns to assign possible classes to new data according to those learned characteristics. For the data set has been pre-processed and was used for the classification model. And the general pre-processing data use the following pre-processing techniques, which would convert drug clones to binary, convert date to datetime, handle missing values, encode categorical variables, scale numerical features. And the features used for the classification model would be any opioid, resident city, sex, age, and race. So the three classification models used for this objective would be the random forest classifier, support vector machines, and logistic regression. So a random forest classifier is a machine learning algorithm that uses an ensemble of decision trees to classify data, making predictions by combining the results from multiple trees. Next, we have the support vector machine, which is also a supervised machine learning algorithm uh, aiming to find optimal hyperplane that maximizes the margin between different classes in an n-dimensional space. Lastly, we have logic regression, which is a supervised machine learning algorithm that accomplishes binary classification tasks by predicting the probability of an outcome event. So basically, all three of these classifies it through different techniques. So it should give a good representation on like how different models would was it perform with this data set. Moving on to the Python codes for classification task. First, we have the code snippet that allows us to import necessary libraries for the classification, and under it would be importing the data set and displaying the head. For the first code snippet, it would encode the y and n values, which is the presence indicator, into ones and zeros, which would help change it into binary format, which would also help the classification models to perform better. Under it would be defining the class, which would be high risk, and the specifications would be that opioid is present and age is over 45. And under that would be selecting the features. So the independent variables would be the resident city, sex, age, and race. And the target variable, which would be the high risk individuals. After defining the x independent variable and the target variable, we will split the data set into the test size of 20%, training size of 80%, with a random state of 42. And under that will be the sampling to prevent what's that data imbalance, which will be the undersampling, oversampling, and smooth. Now we're gonna train the models. First, we will have the random forest classifier. So the code below prints out the metrics of all sampling techniques we used and change the random forest classifier. Next, the code snippet will train the support vector machine classifier, which will also print out three different metrics for the three different resampling techniques used. Lastly, we'll have the logistic regression model. So the code snippet below trains it and also outputs the uh, evaluation metric for all three resampling techniques used. Next, for model validation, I use fivefold cross validation for the models, and I chose the best performing resampling technique for all different models, which would be undersampling for our random forest classifier, oversampling for the support vector machine, and oversampling also for the logistic regression. This will be the result for the performance of all the classification models. So to justify why I chose how I chose the best performing model would be for random forest classifier, the best would be undersampling, which would have an accuracy of 83%. And you can see the precision recall F1 score support for random forest classifier to be more or less the same with all resampling techniques. And the most underperforming model would be the support vector machine with an average of like 55% for accuracy, and the precision recall F1 score support fluctuates throughout the sampling techniques. And a second best would be logic regression, which would have 82% for most accuracy, and precision recall F1 score support is like more or less the same, also similar to the reference classifier. To also measure the performance of the models, we use an ROC curve. So what can we take away from it? Random forest and logistic regression perform the best with an AUC of 0.88, indicating strong predictive power, and SVM struggled achieving an AUC of only 0.65, meaning poor model reliability. Random forest showed a steeper curve, suggesting better sensitivity and specificity. Logistic regression performed similarly to random forest, proving to be strong linear classifier. SVM's curve is closer to the diagonal, indicating a weaker distinction between classes. So the key takeaway for all the model performances would be that Random Forest was the best model, and SVM struggled with imbalanced data, and logistic regression performed similarly to Random Forest with similar scores, and data balancing techniques affected the performance, which would smooth and oversampling improved accuracy, while undersampling led to data loss. So on the left, we have the cross-validation scores for all three key-fold cross-validation for all models, and the best score would be the random forest classifier with a 0.85. So the insight would be that random forest classifier would be the best model due to the highest accuracy, and logistic regression is viable under random forest classifier performing similarly, and SVM has the lowest score, which would suggest that it struggled capturing the dataset. Lastly, for data visualization, is the ratio of the two classes, which will be the presence of opioid and absence of opioid, which is denoted by 0 and 1. It shows imbalance, which is why resampling techniques were used and to improve the model's performance. So you can see that 0 has a higher volume compared to 1.
Hello, my name is Albert Garrison. My student ID is 0362259, and my program is Bachelor of Business Honors. So the problem statement for regression analysis is a difficulty in accurately predicting the number of substance in accidental drug-related death. Most drug-related death involve multiple drugs, which makes it difficult how different drugs contribute to the overall substance use in each case. There are simple ways to do it, like frequency analysis, but it doesn't consider the combined effect of multiple drugs at once, which is why our objective for regression is to develop a regression model that analyzes the contribution of key substances to the total number of drugs detected in accidental drug-related death. We aim to analyze how the presence of the selected drugs contribute to the number of substances detected using regression. Let's start with why we choose regression for this objective and the definition of regression itself. So, why not other method? Well, classification methods, which are designed for categorical prediction, and clustering or association rule mining could identify common patterns. However, they do not quantify the independent effect of each drug on the total substance count, which is why regression is best for this objective. So, regression itself is a statistical and machine learning technique used to model the relationship between a dependent variable, which is the outcome of being predicted, and independent variable, which is the influence that outcome. So the regression models that will be compared and used in this case are linear, ridge, and lasso. Linear is a regression method that shows relationship between variables by fitting a straight line equation to analyze data. The ridge is a more advanced regression, also called as L2 regularization, where the model usually used to address overfitting issue by applying a penalty term as a regularization to correct high-value coefficient. This model will reduce coefficient towards zero. Lasso is also an advanced regression called L1 regularization that improves regression model by shrinking some coefficient to zero, which act as an automatic feature selection. So for the code, first we will import important libraries for developing regression model, and also we will import the dataset. So in this code, we are going to store all the drugs into a list called drug columns, and we will make sure the columns in the drug columns are filled with the numeric of 0 and 1 format. Next, we will make a new target variable was created, which is total substances, which represents the total number of substances detected per case. Next, we will do a correlation analysis as a manual feature, selection of the top six most correlated drugs to be used in this analysis. I will discuss why this is done manually later on. So as you can see, this is the list of the top six correlated drugs. So we will be picking heroin morphine, heroin, benzodiazepine, ethanol, fentanyl, and cocaine. So in this code, the dataset was split into training of 80% and testing 20% subset. This ensures that the model is trained on the majority of the data, while the rest of the data is used for the performance testing. Hyperparameter tuning was performed using grid search CV. This technique tests multiple values for the alpha parameters, which controls the strength of the regularization. The value tested were 0.01, 0.1, 1, 10, and 100. The best alpha values were determined by fitting the models on the training set using five-fold cross-validation technique. This ensures the optimal balance between predictive accuracy and regularization. This code is basically to train the model, and after training, the predictions will be generated, and after that, the predicted values were stored in the predictions dictionary for further evaluation. The model performance use metrics are MAE, MSE, RMSE, and R squared that will be compared later on. This code will do a five-fold cross-validation, which helps to evaluate how well the model generalized to new data. This technique splits the dataset into five different training and test sets, trains the model on each split, and averages the result. Cross-validation will make sure that the model's performance is consistent and not dependent to only one single trained test split. Now let's talk about the metrics. First, MAE calculates the average difference between actual and predicted values, showing how close the predictions are to the real numbers. A lower MAE means better accuracy. MSE measures the average squared difference between actual and predicted values. It tells you how far on average the predictions are from the actual values, but it penalizes larger errors more heavily due to squaring differences. Next, we got RMSE, which is simply the square root of MSE, which makes it easier to interpret as it has the same unit as the independent variable. Lastly, we got R squared, which shows how much the variation in the target variable is, explained by the independent variables. R squared closer to 1 means the model is a good fit for the data. This is the result for comparison of the regression. As you can see, linear regression and untuned ridge regression has the same result of 0.498 MAE, which is quite low considering the range of substance is from 0 to 9, as you can see in the right side. This is a good MAE, and for RMSE, which is at 0.6137, is also considered small, which means the model performs well. And R square is also above zero point 0.6, which is at 0.7234 to be exact, which means the model is good. The untuned lasso, however, did not perform. This is because the features has been manually selected through most correlated drugs, which causes lasso to have nothing to remove and shrink the important predictor and possibly hurting the model. Lastly, the tuned version of Rich and Lasso has a sort of similar result to the untuned Rich and Linear. So in conclusion, linear is the best choice due to simplicity and interpretability. This is a scatter plot which compares predicted versus actual values for each model. The red dashed line represents a perfect fit where predicted values match actual values exactly. Overall, the three models demonstrate a quite similar predictive performance after tuning, with noticeable deviations from the perfect line fit. So linear and rich had an average R-square score of 0.7235, showing reliable performance across different data splits. An optimal alpha for rich was 1, which means only a small penalty was needed to stabilize the coefficients. And tuned lasso regression had a slightly lower R-square of 0.7215. And the best alpha for lasso was 0.01, which also suggests that a small penalty was enough. So, why is Rich and Lasso seems underperforming compared to the simple linear regression? The answer is to prevent data leakage. After a trial and error done, the total substance would have a perfect correlation coefficient of 1, showing a perfect relationship if all the drugs feature was used and we do not do the manual feature selection. So, if we use all the drugs feature, it would mean that there will be zero real world value since it means something is off and the model would not be learning any actual relationship. So, to prevent this, as said earlier, we manually selected the top drugs which made the model more interpretable. However, rich and lasso regressions, which are used to handle multicollinearity and automatic feature selection, will seem quite useless for this case. From these findings, the first and the second place for the drugs with the most influence on the total substances are benzodiazepine and heroin morphine for all the models with different coefficient range. However, ethanol, cocaine, and fentanyl they have a quite similar coefficient in the middle, and heroin will always be at the lowest tier that has the lowest coefficient among the models.
Hi, my name is Sundareswaran Vakishan, and my student ID number is 0359202. Today I'll be discussing the use of anomaly detection in this dataset. To start with, the problem statement. Accidental drug related deaths are increasing, highlighting the need for advanced data driven methods to identify trends and anomalies. This study applies machine learning techniques, including isolation forests, one cloud SVM, DBS scan to detect unusual patterns in demographic factors such as age, sex, race, and ethnicity, as well as substances like heroin, fentanyl, and cocaine. By evaluating the performance of these models using classification metrics such as accuracy, precision, recall, and F1 score, along with clustering validation measures like Silhouette score, Davies Bolden index, and Kolinsky Harabaz index, this research aims to improve predictive models for identifying high risk cases. Our objective for this is the goal of the study is to optimize anomaly detection in drug related deaths by implementing and comparing different machine learning models. Through hyperparameter tuning, the models were refined to better distinguish between normal and anomalous cases, helping to identify key factors in overdose deaths. By providing a comparative analysis of model performance, this research contributes valuable insights to public health, aiding in the assessment and prevention of drug overdose fatalities. Discord focuses on hyperparameter tuning for isolation forest and one class SVM to optimize their performance in anomaly detection. Hyperparameter tuning is essential as it allows the selection of the best parameter combinations for improved accuracy in detection of anomalies. The tuning process is performed using grid search CV, which systematically tests multiple parameter values with threefold cross validation to find the best performing model. For isolation forests, the hyperparameters tuned include n estimators, which determines the number of trees in the ensemble set to 100, 200, and 300. and contamination, which represents the expected proportions of anomalies in the dataset set to 0.01, 0.05, and zero point 0.1. The best model is then applied to the standardized dataset, and anomaly predictions are stored in the anomaly isolation forest column, where -1 represents anomalies and 1 indicates normal cases. Additionally, the decision function where computes anomaly scores, providing insight into the degree of isolation data points. Similarly, one class SVM, the hyperparameters NU, which controls the proportion of expected anomalies, is set to 0.01, 0.05, and zero point 0.1, while gamma, which determines the influence of a single training example, is tested with scale, auto, zero point 0.1, and 1. After tuning, the best model is applied to the dataset, and the predictors are stored in the anomaly 1 class SVM column. This classification helps distinguish normal cases from anomalies while also capturing subtle outliers that may not be easily detected by other models. This code performs hyperparameter tuning for dbScan to improve its effectiveness in anomaly detection. dbScan identifies clusters of data points based on density, making it useful for detecting anomalies as low density points that do not belong to any cluster. To optimize its performance, Grid Search CV is used systematically to test different values for EPS, which is the maximum distance between two samples to be considered in the same cluster, and min sample, the minimum number of points required to form a cluster. The CV equals 3 arguments specifies threefold cross-validation to evaluate different parameters combinations. The best performing dbScan model is then applied to the dataset, and results are stored in anomaly dbScan column. Since dbScan assigns noise points to a label of -1, which is anomalies, and clustered points different positive integers indicating different clusters. The results are converted to a binary format where 1 represents normal data and -1 represents anomalies for consistency with the other anomaly detection models. The last part of the code defines a function, a plot underscore histogram, which generates histograms to visualize the distribution of anomaly scores. The function uses Seaborn's histplot with a kernel density estimation, also known as KDE curve beta, to illustrate the distribution of scores. The function takes in anomaly scores, assigns a title, and customizes the color of the histogram for better clarity in analyzing the spread of anomaly scores across different models. This visualization helps in understanding how anomalies are distributed in the dataset, assessing the performance of dbScan in flagging outliers. This code analyzes and visualizes the anomaly counts detected by the isolation forest, one class SVM, and dbScan models. It first prints the number of anomalies and normal cases for each model by using the value count function on the anomaly labels. Since anomalies are represented as -1 and normal cases as 1, this helps in comparing the proportion of detected anomalies across the different models. The second part of the code generates a bar plot specifically for dbScan anomaly counts to visually display the number of anomalies versus the normal cases. The Seaborn bar plot function is used where anomalies are colored red and normal cases are colored blue for better distinction. The x-axis represents the anomaly labels, -1 for anomalies and 1 for normal, while the y-axis shows the count of each category. The plt.xtext function customizes the x-axis labels to clearly indicate the meaning of each category. This visualization provides insights into how dbScan classifies data points and the proportion of detected anomalies, which is useful for evaluating the performance in detecting unusual patterns of drug-related death cases. Comparing the anomaly counts across different models also helps in understanding their sensitivity to outliers, determining which approach might be the most effective for identifying the significance in outliers in the dataset. This code evaluates the performance of the isolation forest and one class SVM models using standard classification metrics and assesses the clustering effectiveness of dbScan using clustering validation measures. Binary classification model evaluation for the isolation forest and one class SVM. The function evaluate classification model calculates and points key evaluation metrics. Accuracy means the overall correctness of anomaly classification. Precision assesses the proportion of correctly identified anomalies out of all the predicted anomalies. Recall, also called sensitivity, measures how well the model detects actual anomalies. F1 score is the harmonic mean of precision, and recall balancing both metrics. This function is applied separately to isolation forest and one-class SVM, comparing the predicted against anomaly labels in DBSCAN. The choice of DBSCAN as a ground truth helps assess how well these models agree with the density-based clustering approach in detecting anomalies in drug-related deaths. Clustering evaluation for DBSCAN. Since DBSCAN is an unsupervised clustering method, traditional classification methods do not apply. Instead, three clustering evaluation methods are used. Silhouette score measures how well clusters are separated. High value indicate better defined clusters. The Davis-Bolden index evaluates the similarity between clusters. Lower values signify better clustering. Finally, the Kalinske-Harabaz index assesses the ratio between cluster dispersion to within cluster variance. Higher values indicate more distinct clusters. These metrics are only calculated if DBSCAN detects more than one cluster. This results help determine whether DBSCAN effectively distinguishes anomalies from normal drug-related cases. So I'll be discussing the justification for model selection. Isolation forest was chosen because it isolates anomalies through recursive partitioning while making it effective in detecting rare cases by polysubstance overdose deaths involving uncommon drug combinations. However, its low recall indicates that while it's effective and identifies extreme anomalies, it may miss more subtle cases. One class SVM was used due to its ability to learn normal patterns and flag deviations based on hyperplane, making it suitable for detecting nonlinear relationships in drug combinations. For instance, heroin and fentanyl together might be common, but the addition of benzodiazepines could create an anomaly. Despite its precision, its low recall suggests it overlooks many deviations from typical polysubstance use. Finally, DBSCAN was selected for its ability to group data points based on density, identifying clusters of overdose deaths that share similarities yet differ from the majority. It helped detect cases where fentanyl and xylazine appeared together, but without heroin. However, the lack of clear clustering indicates that drug-related anomalies may not form well-defined density-based groups due to overlapping substances use patterns. In evaluating the performance of our anomaly detection models, we focus on isolation forest, one-class SVM. Since isolation forest and one-class SVM are unsupervised models, we compare the predictions with DBSCAN results, assuming DBSCAN serves as a reasonable reference for anomalies. The accuracy for forest and one-class SVM were 85.33 and 85.53% respectively. While these values indicate that most classifications were correct, accuracy alone is not reliable metric due to imbalance in normal and anomalous cases. Precision, which measures how many predicted anomalies were truly anomalies, were exceptionally high, 100% for isolation forest and 96.75 for one-class SVM. This suggests that these models flagged an anomaly that were highly confident. However, this came at a cost as shown in their low recall scores of 6.39 and 7.93. The low recall indicates that both models failed to capture a significant portion of actual anomalies, likely because drug-related deaths involve complex and overlapping factors, making anomaly detection challenging. The F1 scores, which balance precision and recall, were quite low, 0.1201 for isolation forest and 0.1467 for one-class SVM, highlighting that while models were precise, they were overly strict and missed many true anomalies. For DBSCAN, we use clustering validation metrics to assess its effectiveness. The silhouette score was 0.2453, which suggests that the detected anomalies did not form well separated clusters. This aligns with the reality that drug-related deaths do not always have clear distinctions between normal and anomalous cases. The David-Bolden index was 4.5557, indicating poor separation for anomalies from normal cases, further reinforcing the idea that the substance use patterns are highly overlapping. The Kalinske-Harabaz index was relatively high at 388.2520, suggesting that the DBSCAN was able to form measurable clusters. The anomalies did not fit neatly into distinctive density-based groups. This suggests that DBSCAN may not be the most effective method for detecting anomalies in a drug-related deaths, as the nature of substance use does not conform to well-defined clustering structures. Overall, while isolation forest and one-class SVM provided highly precise anomaly detection, they failed to capture many actual anomalies. DBSCAN, on the other hand, revealed that drug-related anomalies do not cluster in a way that traditional density-based methods can easily separate. This highlights the complexity of identifying anomalies in accidental drug related deaths, while multiple factors interact in ways that they do not always follow clear statistical patterns. The histogram of isolation forest anomaly scores in right skewed, meaning most cases have low scores with fewer high score anomalies. In the normal cases, where most deaths have anomaly scores between 0.05 to 0.15, indicating they follow well-known overdose patterns. Example, opioid-related polysubstance with benzodiazepines or stimulant-related deaths. Moderate anomalies, cases with zero point 0.2 to 0.25 anomaly scores may indicate emerging drug use trends, unusual demographic patterns, or overdose in clusters in unexpected locations. Extreme anomalies. The rare case with very high anomaly scores represent unusual drug combinations, synthetic opioid, rare depressants, or unique demographic factors that significantly deviate from known patterns. The right skewed nature of this histogram shows that most overdoses follow an expected patterns, while a few rare cases with high anomaly scores emerge due to isolation forest partitioning method, which isolates common cases slowly and anomalies quickly. Finally, a significance of anomaly scores. These scores provide insights into overdose trends and help public health agencies identify new risks evolving drug use patterns and potential data recording errors or novel medical conditions. Here we have the histogram of the one class SVM. So to begin with, the distribution and skewness analysis. The histogram is right skewed and mostly anomaly scores between zero point 0.5 and 1.0, indicating normal cases. Few cases have negative scores, suggesting extreme outliers classified as rare by the model. A sharp drop off beyond 1.5 anomaly scores shows that true extreme cases are rare. And finally, as an interpretation, what we can understand is most drug related deaths follow expected overdose patterns aligning with past studies. Lower scoring outliers likely indicate uncommon drug interactions, and rare demographics a unique overdose mechanism. The model identifies unusual polysubstance combinations or underrepresented groups as anomalies. Finally, the comparison with the histogram of isolation forest, we understand that one class SVM assigns anomaly scores within a narrower range than isolation forest. It is less aggressive at detecting anomalies, meaning it reduces false positives but has a low recall. Precision is high at 0.9675, but recall is low at 0.0793, confirming that while the model is accurate when it flags anomalies, it misses any actual outliers. Unlike isolation forest, one class SVM relies on a boundary based approach, leading to a concentrated normal score distribution. The bar plot represents the classification of drug-related deaths by DBSCAN, where normal cases label 1 are shown in blue and anomalies label -1 in red. The y-axis indicates the frequency of occurrences, revealing that approximately 80% of the data sets was classified as normal, while 20% was identified as anomalous. DBSCAN, as a clustering-based anomaly detection method, groups closely packed data points and labels those in low-density regions as anomalies. In this case, the detected anomalies likely involve unusual drug combinations, rare demographic factors, or unexpected overdose circumstances. A typical heroin or fentanyl overdose would be categorized as normal, while overdoses involving rare synthetic opioids or uncommon polysubstance interactions might be flagged as anomalies. Other contributing factors include demographic outliers, such as overdoses occurring in age groups or racial groups that are underrepresented in dataset, and environmental factors like overdoses appearing in unexpected locations. These anomalies could signal emerging drug trends, new synthetic substances, or unique overdose scenarios, warranting further investigation. Unlike isolation forests and one class SVM, which assumes a prior distribution of normal data, DBSCAN identifies anomalies based on their spatial isolation. This makes DBSCAN effective at detecting localized anomalies, such as drug related deaths that deviate within specific subgroups that are not globally rare. However, it may not detect dispersed anomalies as efficiently as isolation forests. The detection of around 20% of cases as anomalies suggest that a significant portion of drug related deaths exhibit non standard patterns, making DB Scan a useful tool for identifying potential new overdose risks, monitoring evolving drug trends, and guiding public health interventions. In conclusion, the analysis using isolation forest, one class SVM, and DB-Scan provided valuable insights into accidental drug-related data set. Each model identified anomalies differently, contributing to a broader understanding of outliers. Isolation Forest and One Class SVM used a global approach, with Isolation Forest detecting anomalies based on feature distributions and One Class SVM identifying cases outside a normal decision boundary. While these models were highly accurate, they may have missed some potential outliers. Finally, DB-Scan, using a density-based clustering approach, flagged about 20% of cases as anomalies, indicating uncommon overdose patterns unlike the other models. DB-Scan does not assign anomaly scores, making it less useful for ranking anomalies but effective for detecting them. Thank you.